All right, so welcome back, ladies and gentlemen. This is the second part, the second video of using Coulomb's law. So this is for the second page, and hopefully you've gone through the first video and practiced kind of the first two questions at the top of this page in your Google Doc. So let's get started into question number 3. So in this particular question, I have 3 charges again. You're going to find that pops up a lot, just going to help us practice. So I have 3 charges in a line. Okay. Now the charge of these, the leftmost one, has a charge of 3 nanocoulombs. I'm just going to refer to that as Q1. The one in the middle, Q2, has a charge of 2 nanocoulombs. And remember, nano is 10 to the negative ninth. And then the charge all the way on the right side has a charge of negative 5 nanocoulombs. Okay. Now, this question wants us to figure out what the acceleration due to the net electric force on the sphere in the middle is. Okay, and that's a lot of science words. Literally, what it comes down to is I just want to figure out how fast the sphere in the middle is speeding up. Okay, now all 3 of these spheres are 2 kilograms, and we are only, for the sake of this particular question, we are only going to worry about electric force. Okay, there's going to be a problem later on where you're going to see why we can ignore gravity, because I promise we can't. So, just like we do in any other question, we start by drawing an FBD. Okay, so if you can, pause the video here, take about 90 seconds, however long you need to, draw the FBD for the middle sphere. So that's the 2 nanocoulomb sphere. Okay, hopefully you took some time to draw that FBD. So looking at the sphere in the middle, it is experiencing 2 forces. Okay, so let's start with the one that's closer to it, the 3 nanocoulomb sphere. All right, in that case, they are both positively charged spheres, so they're going to push away from each other. So the 3 nanocoulomb sphere is going to push the 2 nanocoulomb sphere to the right. So we're going to start by having one force going to the right. I'm just going to call that F12. Okay, and just to make sure that we aren't getting confused, this is Q1, object 2, object 3. Now, the other object that is applying a force to the sphere in the middle is the one all the way to the right. And this time, they are oppositely charged. This is negative, this is positive. So they are attracting each other. So this one, the sphere to the right, is actually pulling the 2 nanocoulomb sphere to the right. So this second force acting on it is also going to the right. And it's going to be F, just going to call it 2, 3. All right. Now, this question is just basically taking what we did previously in the first page and just going one step further. So once I have the FBD, the next thing I want to figure out is I want to find Fnet. Okay. Now, in this case, once again, looking at the FBD, these 2 forces are going the same way. So the net force is going to be the 2 of them added together. So your task is to literally just calculate the electric force between 1 and 2 and the electric force between 2 and 3. Okay? Now, just remind yourself when you do this, before I let you go, Coulomb's constant, 8.99 times 10 to the 9th. Q1 is going to be the charge of the first object. Q2 is the charge of the second. When you see that nano, that's 10 to the negative 9th. So Q, in this case, the charge of the 3 nanocoulomb sphere would be 3 times 10 to the negative 9th. Okay? So, at this point, if you could please, ladies and gentlemen, I want you to pause the video, and I want you to solve for what the net force is on the middle sphere. Okay? Now, if you've had a chance to find the net force, what that's going to look like is something like this. So, we already do the FBD. If you find the net force, I do the calculations right here, so they're off to the left side. The force between 1 and 2 is going to be very small. There's not a lot of charge on these spheres, so the force is quite small. So in this case, between 1 and 2, the force is really small. It's 8.63 times 10 to the negative 7th. All right. For the charge between the second and the third spheres, that is going to be a force of 1.6 times 10 to the negative 7th newtons. And one thing that's really important that I want y'all to kind of focus on is that if you're getting the right numbers here, but your exponent is wrong, it just means that you're going to have to get the parentheses right. Okay, and that can be really annoying to deal with at first. Just make sure everything is in parentheses so that your calculator knows what order you're going in. Okay, and just remember, as always, that absolute value sign is just there because it makes our lives easier when we actually find the net force. Okay, so those are the two electric forces. We know the net force is those two added together because they're going the same way according to our FBD. So if we add these two numbers together, we get that the net force is 1.023 times 10 to the negative 6 newtons. So it's still a really small number, and it's pushing it to the right. All right. Now, once we know the net force, all we have to do now to answer the final question is we need to find the acceleration. And if we know the net force on an object, and we know its mass, which in this case we do, it's 2 kilograms, then we can use Newton's second law to find acceleration. Okay, so if you want to find it for yourself, pause the video here, use Newton's second law to work this acceleration out, and then once you got it, unpause it, and we'll talk about what the answer is. All right, so hopefully if you had a chance to work through this, we know the net force is what we found over here, 1.023 times 10 to the negative 6 newtons. All right, acceleration is just net force divided by the mass. So take that really small number, divided by 2. So we get that the acceleration of the middle sphere is going to be 5.115 times 10 to the negative 7th meters per second squared to the right. Okay, and awesome. There's a lot of numbers here. It shows that we're great at calculating things. Honestly, what this tells us and what it means in the real world is that if you have a tiny bit of charge on something, it does exert a force, but as you can see in this case, the acceleration is so small that honestly, it's not noticeable. Okay, so just something interesting to see is that charges, depending on if we have them at real world scales, I mean, this is 25 centimeters, it's not that far away, but it's still a normal distance. The force between all these things is minuscule. All right, so that's it. That's the answer for question 3. Now, let's look at the last question on this. Okay. So for the last question, I have 3 charges again. And it always seems to be multiple charges just lined up in some basic shape. All right. So this is shapes practice. In this case, they're set up kind of like a triangle. Okay. Now, I want to once again figure out the net force acting on one of the charges. In this case, I want to find the net force acting on this charge right here. Oh, look, I drew a little eye. How exciting. The other thing we're going to want to figure out after that is what direction, that's the same thing as saying what angle the net force is acting at. Okay. Now, I've broken this down into 3 questions here. The first is draw the FBD. Okay. The second part is I want you to calculate the vertical and the horizontal force acting on this charge. All right, so basically find Fy and Fx. And then the final piece is we're going to use these 2 things to figure out the net force. Okay, so right now, what I want you to do is I want you to do the first 2 parts. I want you to draw the FBD. I'm confident enough now that we've done enough practice that we can answer this first 2 parts on our own pretty easily. So draw the FBD, please, and then calculate the amount of force in the y direction and the amount of force in the x direction. Okay, and then we'll come back together and talk about how your answers look and how to do the final part.